All right. So in the last lecture in this series, I'm going to start by kind of recapping and reviewing what we've learned about dark matter from the sorts of searches we've talked about, and I'm going to try to fill that in because there are a lot of indirect searches that I haven't been able to talk about in these few hours. So I'm going to try to kind of summarize the landscape here, and then we're going to turn to the features that models might have that might turn us away from this benchmark we've been talking about here the whole time. Which I'm going to maintain the position that this is a pretty good benchmark, but we shouldn't assume that that's where dark matter lies. In fact, it's very, very easy, as we'll see, for dark matter models to lie above or below this curve. All right, so let's start with the ones that we've talked about. So we have a constraint, for example, from dark matter annihilating in dwarf galaxies. And this is about the approximate answer. So that's Fermi constraint on stacked dwarfs for a BB bar channel. I am going to now write a second line in a color for the case of the tau channel. So they're not that different. They vary a little bit. The main thing is when taus are produced, they annihilate to a lot of hard photons, basically because those taus produce neutral pions in every step of their cascade, and sometimes multiple ones. Bs make a little bit softer gamma rays, but they're not that different. If you look up the constraints for other kinds of quarks, or for Ws or Zs or Higgses, you get constraints that are pretty close to this BB bar curve. So you can think of this as a proxy for most hadronic or gauge boson, Higgs boson channels. The real exceptions are if you're annihilating to things like electrons, muons, or neutrinos. Those give you very different constraints, much significantly weaker constraints. So next, let me write on here, I'll do it in yellow, the constraints from anti-protons as measured from by AMS, again for the BB bar channel. Here, the constraints are very strong at low mass. They look something like that. That's maybe too steep. Something like that. Okay? So, taken at face value, this provides by far the strongest constraint on dark matter lighter than maybe 20 GeV or heavier than a couple hundred GeV. But I think it is entirely fair to say there should be a band around this, having to do with the ignorance we have regarding a lot of the antiproton production cross-section stuff, as well as the transport through the Milky Way. So unlike dwarfs, which are pretty clean, I would put a healthy systematic error bar around this constraint. And next, if we're talking about leptonic dark matter, like for example, dark matter annihilates mostly to E plus E minus, the constraints from AMS and the positron fraction are very strong. Something like this. And I can do the same thing for muons or taus. Something we haven't talked about at all, but I would be remiss to not mention, is that if dark matter is light and annihilates efficiently in the early universe, it can have substantial impact on the process of recombination. So in other words, around the time that the CMB is forming, all this dark matter is annihilating, producing stuff that can go and reionize or prevent from recombining all these hydrogen atoms. So that can have a measurable impact on the CMB. The current constraints, this should be 27. The current constraints on that look something like this. For a wide range of channels. Not everything, though. These are constraints if you're not going to neutrinos. If you're going to electrons, it's a little bit stronger, but not as strong as the AMS constraints. So, in the very worst case scenario, you can imagine that the dark matter annihilates uniquely to neutrino pairs. If that's the case, then the constraints are much weaker. And ice cube constraints for a nu bar final state are roughly in this sort of range, okay? They're very weak. They can't probe a thermal relic, but they're not zero, okay? So this is, in a very nutshell sort of way, what we've learned about dark matter. So if we're talking about something that is largely hadronic in its interactions, we know that the dark matter, if it's a strict thermal relic of the simple velocity-independent kind, we can say that it's either going to lie in this sort of window here, okay, around a few tens of GeV or maybe up to 100 GeV, or it's going to be above several hundred GeV. Okay, those are the sort of windows that are left. If it's more leptonic, the constraints are generally stronger. Basically, you want to force it to be a couple hundred GeV or more. Generally speaking, the lighter you get, the stronger these constraints are, and the more you'd have to depart from a simple thermal relic. Any questions on this before we start talking about the features that we might expect models to possess? Okay. So I've been talking about these annihilation channels as if they have no connection to anything, as if they're just handed down by God to physicists like us, phenomenologists. But you can say some general things about what broad classes of models say about how dark matter should annihilate. So let's start with a case and just say what we can generically say where the dark matter is lighter than things like the WZ and Higgs. So we can really basically only annihilate the fermions, at least within the context of the standard model. At tree level, I could imagine some sort of S-channel diagram. And I'm writing this could be a scalar or a vector. Or, of course, I could consider some sort of, I'll just draw a solid line. I'm not trying to be specific about the spin of anything here, really. Okay, T-channel or S channel. So let's kind of just say like what we expect from a broad sweeping, plenty of exceptions sort of way about what we'd expect the annihilation fractions to go into the various kinds of fermions. Well, we could easily imagine in a case like this that the couplings are proportional to M fermion. Okay, that's an easy thing to write down. These could be Yukawa couplings of some sort, or maybe it's Higgs mediated, something like this, in which case you would expect these annihilations to predominantly go to the heaviest of the kinematically available fermions. You could also easily imagine some sort of scenario where the annihilations are roughly democratic. The couplings to various fermions are all of the same order of magnitude, or maybe there are several of them that are of the same order of magnitude. This really would come down to some sort of choice of charge assignments, for example. That's very easy to imagine. So yeah, I forgot a C in that, democratic. You could easily imagine models like that, or lots of those. And then thirdly, I'll just note, if the dark matter is a Majorana fermion, then the low velocity piece of this cross section is going to go like M fermion squared over M dark matter squared, no matter what the couplings look like. This is just a matter of chirality suppression and is a generic feature of any low velocity annihilating Majorana fermion.
So what's going to zero in that?
Velocity in the low velocity limit as relevant for indirect detection. That doesn't necessarily mean it frees that it will behave that way, but in the galaxy or wherever else today, the annihilations will be suppressed to light fermions. So now you can begin to see why so many dark matter constraint plots focus on things like BB bar or tau plus tau minus. If you have a dark matter particle that is lighter than the thresholds for WZs and Higgses, the heaviest available fermion will generally be the B. That's why BB bar is so popular. And then tau, if you have something where maybe you're coupling to hypercharge or to leptons or something like this, those become quite important.
Isn't a key and relatively important factor going to be what that mediating thing is? Will that dictate what it is?
Well, I'm trying to remain pretty agnostic about the underlying model. I'm trying to discuss like thousands of models in a few sweeping statements. And that's, of course, not a thing that you can ever make blanket statements about. But, when I say the couplings are proportional to the fermion, what I mean is the mediators couplings are. That's kind of a generic feature of many scalar, for example, mediators, Higgses and such like that. Democratic would be something you generically expect with some sort of new gauge boson, for example, or even an existing gauge boson. So yeah, these are really coming from features of the mediator, but I don't want to specify exactly what I'm talking about. All right, so in the T-channel case, it's quite different because whatever this is has to carry the quantum numbers of the fermion, or perhaps the dark matter does in the flavored dark matter case. But that mediator carries some combination of charge or color or baryon number, lepton number, things like this. And as a result, exactly what kinds of T-channel mediators exist can very much determine the outcome of the annihilations. For example, I could have a model where the only relevant mediator carries tau number, okay? And then the only annihilation product will be a pair of taus. I could very easily imagine a scenario like this where annihilations are dominated by one choice of fermion final state, and that could be just about anything. I could also imagine a case where there are 3 generations of these T-channel mediators, and therefore I get all sorts of final state fermions. It's really extremely model dependent, but it just opens up the range of possibilities considerably. And then there's not much to say about the reverse case, where the dark matter is heavy enough to go to these sorts of final states, except that those states can, in many cases, dominate. So you end up with W's, Z's, Higgses, and various combinations thereof. That happens in a wide variety of models if it's kinematically accessible. One reason I haven't drawn a lot of limits for those sorts of annihilation channels is when you produce W's and Z's that are boosted or something, they decay down to things that mostly look a lot like the sort of jets that we're talking about from hadronic states. So, a W, the vast majority of the time, 70% of the time, decays to a pair of quarks, which looks a lot like as if you had annihilated the quarks in the first place. Not exactly, but a lot like it. There is one annihilation.
Just a question like semantics. So if you annihilate the quarks via a W, virtual W, you violate the only difference between if you have a W that decayed is that it's not virtual necessarily.
So if I do this, right?
I see you have 4 quarks of it.
Yeah, and the quarks are boosted in a different way. So they actually do lead to different spectra of annihilation products. But you can do this. You can put this in Pythia or your favorite tool of choice and get the right answer. It's entirely tractable, but it's just not very different in outcome than if I had been talking about direct annihilations to quarks, for example. So there's one annihilation channel that I think is worth mentioning that doesn't fall into any of those categories, and that's scenarios in which the dark matter directly annihilates to a pair of photons, or maybe a photon in another particle. Okay, so like a photon in a Higgs or photon in a Z, something like that. The reason this is interesting from an indirect detection perspective is that every time that annihilation happens, the photons that come out have exactly the same energy. So it's a monoenergetic gamma ray line feature that this will produce. And that's a lot easier to see. Okay, so you might not understand your backgrounds, but you can look at your gamma ray spectrum of an object like the galactic center or the galactic halo, and you can make statements about the lack of bumps. And the lack of bumps can be used to place very strong constraints. But the problem is that these sorts of annihilations very rarely dominate in dark matter models. In fact, they almost never do, and there's a good reason for that. if I wanted to write down a tree-level diagram that went to a pair of photons, I mean, this doesn't make a lot of sense in the first place, but generically, whatever's involved in this diagram, there has to be something charged. And you can just see immediately that would make your dark matter charged in a way that doesn't make any sense. You just can't write down any sort of diagram at tree level that gives you a pair of photons. So we have to do this at loop level instead. So I can just write down a few examples of the sort of loop diagrams that might give you a gamma ray line. So here I have in mind some sort of charged particle loop that couples to some sort of mediator. That's the sort of thing one can easily write down. I can also write down something like this, where you have scalars mediated by some sort of charged scalar loop going to a pair of photons. And then just as a third example, and this is by no means inclusive or exhaustive. I don't know why that's okay. I have some sort of charged partner of the dark matter here. Okay. But the generic features have to be some sort of new charged particle loop that does the work. And because there's this extra loop, you're suppressed by a loop factor, and you tend to get annihilation cross-sections to photon lines that are maybe 3, 4, 5 orders of magnitude smaller than the annihilations cross-section to other states. Now there are exceptions to this. You can try to bump this branching fraction up. Like so, for example, I could imagine taking a diagram like this and just postulating that if mx is less than mw and m charged, then the only kinematically accessible final state might be a pair of photons. Okay, so that's a sort of thing you can do, and then you can get large line signals. But in general, or at least generically speaking, you do not expect particularly large annihilation fractions to line features. But if you did, you would expect strong constraints. So Fermi looking at the halo. Again, this is in cubic centimeters per second, like we've been doing. The constraints are extremely strong. They're roughly in this sort of range. Okay. So 10 to 31 is 5 orders of magnitude lower than the sort of cross sections we've been talking about. These are very, very strong constraints. So we can at least say that whatever is causing the dark matter to deplete in the early universe, it's not significantly going to these sorts of line-like final states. Fermi. This is Fermi, looking at the halo of the Milky Way. So I'll just generically say the more distinctive a spectral feature you're looking for, like a line, the more you want to open up your region of interest in an analysis like that. If you are concerned about your backgrounds, as you might be with a less distinctive signature like this, you might want to look where the signal to background is the highest. But if you're looking for a very faint signal that's very distinctive, you're better off opening up your ROI, your region of interest, and looking at collecting more photons over a larger part of the sky. That's why they look at the halo and not just the galactic center, not just dwarf galaxies. Okay, so that one's not working. Now I'm just going to give you a laundry list of ways in which a dark matter might very plausibly annihilate with different cross sections in this benchmark we've been talking about. The last thing I want is for you to walk away from these lectures thinking 2 × 10⁻26 is magic, and that's the thing that if we rule out WIMPs. That is not true. There are lots of ways to get different numbers in this, and I'm just going to show you some of the easiest or most popular, most often found across the model space. So generically, we can write down whatever this cross-section is as a Taylor expansion in powers of v squared. P-wave amplitudes contribute to the v squared and higher order terms. S-wave amplitudes contribute to all of the amplitudes. So sometimes people talk about a velocity that is, or a cross-section that is not velocity suppressed as an S-wave annihilation cross-section, and sometimes they talk about one that goes like v squared as a P-wave annihilation process. The language is sometimes used in a little bit of a sloppy fashion, but that's what people oftentimes mean. I will just draw a quick chart here. Here I have in mind dark matter that is a fermion, and it's going to annihilate through some sort of S-channel diagram. Here I'm going to write various dark matter bilinears that I could consider. So I have a scalar, a pseudoscalar, a vector, and an axial case. Okay. It's reasonably exhaustive. Of course, you can have various combinations, but and then up here, I will write down the various bilinears you could have with the final state fermion and the mediator. Again, from left to right, scalar, pseudoscalar, vector, and axial. And the cross sections scale as follows. These don't make sense. Okay. So I don't have time. I was originally going to go through a few of these cases and show you. Which one? Yes, you're right. That doesn't make any sense. Thanks. That's what I mean, right? Okay, so you can work these out on a few lines in many cases, but I wrote twice as many notes as I had time to get through in these 5 lectures, so that had to go. But this gives you a flavor for a range of scenarios you might write down. And the point is that, an order 1 fraction of these are P-wave suppressed, and an order 1 fraction aren't. That's not uncommon. If I wrote down all of the simplified models one could consider, with various combinations of spin and couplings and interactions, you would find something similar. This isn't cherry-picked. So you have no reason to think that a generic dark matter model will always give you a low velocity annihilation cross-section. Why are they nonsensical?
So my point is you've got all the other ones, but you've got like the 2 V's and the 2 dashes where this makes no sense. They're both squared for the first one, both 0, and then you've got the 2 and a 0 for the last one. I don't know what makes that one different. The velocity dependence is so different for those 2 cases. So
when you have a combination of a vector coupling here and an axial coupling here, why do you get v squared? Is that what you're asking?
And then v0 for the other one because you don't get v squared for one other.
That's right. I don't think there's any reason to think that these have to go together. Well, I mean, okay, so you have 2 different cases. You shouldn't expect them to be alike. Okay. I don't have off the top of my head a clean 1-sentence explanation for why it works out that way. I've done the calculation, and lots of other people have. And maybe if I thought more deeply about it, I would have like a punchy answer. These are more. These tend to be just features that I derive and then memorize. There probably. I mean, I'm sure there is a deep reason, but I do not have it at the tip of my fingers. So, sorry. The table doesn't what? It does not have to be symmetric. There probably are symmetries built into that, but it's not the most obvious one that you would imagine, or you might look for. So if we have something with a v squared cross section, the cross section that's relevant for indirect detection, that's IND for indirect, over the annihilation cross section that's relevant for thermal freeze out are very different. Because in the halo today, typical dark matter particles are moving around at 10 to the minus 3 of the speed of light. And at freeze out, the velocity squared was about 0.1 or 1/10 of the speed of light squared. And that's a big number. So if I just have a P wave relic, I look at this plot, I'm not testing anything, okay? Indirect detection, as it currently stands, is not sensitive to anything in this mass range if it's, strictly speaking, P wave suppressed. Now, if it has a small S-wave piece, or small S-wave amplitude, then this story can change. But a pure P wave amplitude is not particularly strongly suppressed at this point. You don't have to assume that. It applies to both. I mean, some of these you can't write down if it's a Majorana, right? You can't write down a vector coupling for a Majorana fermion. Yeah. No, actually, v squared is 0.1. Yeah, it is. I wrote what I meant. You were totally reasonable to guess that I didn't, but I did. All right, so let's just do a quick estimate, and this is not going to give you exactly the right answer, but it gives you something close. So the total power that's produced in dark matter annihilations, of course, scales with the cross section over the mass squared. So this is the annihilation rate times the mass, because per annihilation, the amount of power is proportional to the mass. Okay, so this is a rough scale of how much power is going to be produced in the halo. So if we are currently constraining things with an S-wave amplitude up to, say, 100 GeV or something, and we're going to reduce this by 5 orders of magnitude, that means the mass scale, which will produce a similar amount of power, will be 5 orders of magnitude below 100 GeV, which is about an MeV. So in other words, indirect detection, if assuming equal power is equally detectable, which is a bad assumption at a factor of a few, but it's a good back of the envelope, indirect detection is roughly sensitive to MeV scale P wave thermal relics, which for the BBN reasons we talked about before is not as interesting as we'd like it to be. All right, so going on. So one way we just showed to suppress the indirect detection signal is to consider a P wave relic. But another way is to imagine that the dark matter annihilates through some sort of mediator on resonance, by which I mean twice the dark matter mass is similar to the mass of the mediator. So I'm just going to write down a plausible form for such a cross section. Alpha is just the overall normalization. You can think of it as analogous to alpha EM. And then I have the standard resonant behavior down here, including the mass and width of the mediator. So this is going to look like something like that. It's going to fall with S with a big spike at the resonance. value of S at low velocities is just four mx squared. And the value of S at freeze out will be about 10% higher. So I can imagine now two very different scenarios depending on exactly what these masses are. In scenario A, I could say the mass of the mediator really is very close to the mass of the dark matter, or twice the mass of the dark matter squared. In other words, today, for the purpose of indirect detection, you're right on resonance, and the cross-section will be big. But at freeze out, S was a little bigger, and the cross-section were much smaller. Yeah? V goes to 0. So that is relevant for indirect detection. So I think you can see intuitively what's going to happen in this case. In this case, the annihilation cross-section today will be strongly enhanced relative to what you'd get from the generic thermal relic estimate, because the cross-section at low velocities is so much bigger than at freeze-out velocities. So I'm going to skip some of the steps. But in this particular case, this ratio works out to be the following. Okay, so if the width is very large, this just works out to 1. That just means the resonance is smeared out and you don't get any effect. As the width is smaller, however, this enhancement gets very large. So let's put in some examples. These are based on something like the Z, but you could put any numbers you like. For those particular choices, this ratio,
Oh, it's 25.
2.5.
No, 2.5. So, oh, right, I'm with you.
Okay. For this particular choice, this ratio works out to about 13. In other words, the cross-section you should expect today is not 2 times 10 to the minus 26, but 2 times 13 times 10 to the minus 26. Okay. So a few times 10 to the 25. And then looking at this chart up here, for most of these annihilation channels I'm talking about, you would rule out everything up to probably a TeV or 2, okay, for such a case. So scenario A is the positive one, the one that makes indirect detection powerful. Let's consider another case. So I'm going to make the mediator now just a little heavier than the low velocity resonance. So drawing this again. In this case, indirect detection is going to be dictated by something off resonance, while freeze out is dictated by something that takes place on resonance. And in this case, you get approximately the following. So again, if the width is large, this is not a big effect. If the width is small, it's a very big effect. That's exactly what you would expect. And if I use my same benchmark parameters I show here, I get a suppression of about 3 orders of magnitude. So, looking at, well, if you could see the chart that we're covering up right now, you'd find with 3 orders of magnitude suppression, you're really not sensitive to this class of models. Now, it's a little tuned. You know, it requires a 10% tuning. I can live with 10% quite comfortably, but you know, it's maybe not the single most likely thing to happen, but it's not implausible at all. And you could imagine lesser tunings leading to lesser suppressions that are maybe a factor of 3, 10, 20, whatever. Those are extremely common.
So most of the things that we've seen have been saying that okay, no wait, so in case A, that would be saying that we should see, for indirect detection, we would expect to see a cross-section that is significantly larger.
That's right.
We have not seen such a thing. Isn't this a problem in case A?
Well, like I said, like if you took the case A at face value, and just said, well, just in general, like there's a factor of 13 or something enhancement, you would rule out most of the parameter space up to masses of 1 or 2 TeV. But you could still have a multi-TeV WIMP that lived on a resonance of that kind. That would still be okay. But you're right, the constraints get stronger and you're forced to different sorts of parts of parameter space. All right, so that was resonances. We talked about P-wave suppression. The next is going to be co-annihilations. And what I mean when I say that is that the dark matter annihilates not in pairs, but along with some other state that isn't itself stable, but that carries some of the quantum numbers that allows it to annihilate. Okay. So like in supersymmetry, for example, you might have a scenario, just if you have intuition about supersymmetry, you might have a scenario where the neutralinos, the light is the dark matter, but its annihilation cross-section is quite small. And if that were the whole story, it would be produced in far too great an abundance, and therefore we'd overclose the universe or otherwise exceed the dark matter abundance we measure in the universe. But there's a second superpartner with a similar mass, not much heavier than the lightest neutralino, and they can annihilate in pairs, conserving our parity, but depleting the abundance through these co-annihilations as opposed to dark matter annihilations. Is that clear? So let's just...
So it's annihilating, it's antiparticle?
That's correct. So common examples in SUSY would be neutralino chargino co-annihilations, or neutralino stop co-annihilations, or neutralino Stau co-annihilations. These are all the sorts of things that are commonly talked about in the literature, although less and less these days as LHC puts pressure on such scenarios.
There's no examples of this happening in Sarah.
That's a good question. I mean, I guess you can write down neutrino charged lepton annihilation diagrams. That would be perfectly fine. I don't know that they're particularly important, but yeah, you could do that. Just for example. Okay, so at freeze out, we can write down the number densities of these two states. So they're still at or near equilibrium, so we can just scale this with the equilibrium number densities. And everything cancels with the exception of the parts and the exponents. There's some stuff having to do with degrees of freedom too, but I'm taking all of that to be order 1. So I'm going to say the temperature of freeze out is the dark matter mass over 20, which is about right for a wide variety of sort of WIMPs. And when we do that, we find that this reduces to the following. Okay. And you can kind of see where I'm going here.
Do they temperature? If so, why?
So what I have in mind here is that we're at a point, well, okay, it's going to depend. We could imagine, for example, okay, what I mean by the freeze out is the total number of both types of species, whatever carries the stabilizing quantum number, okay, that total population has not frozen out yet.
Okay.
And you'll see some different examples of that in the lines ahead. And it is the case we're going to talk about two particles with similar masses. So for that reason, we expect them to freeze out at similar times. Okay. So let's consider a couple of cases. Let's imagine one where the co-annihilating state is maybe twice as heavy as the annihilating state. Then putting in the 2 for that ratio up there, I have that this works out something very, very small, like 10 to the minus 9. Okay? So that means when our dark matter candidate is freezing out, for every dark matter particle there is 1/billionth on average of co-annihilating particle, and that just doesn't matter. Okay? You can entirely ignore that. There is no effect from co-annihilations when the mass splitting is as big as a factor of 2. Okay, so I wrote that down just to make it drive home the point that this only matters when there's a close degeneracy in mass. In this case, as an alternative, let's say there's a 10% mass splitting. In this case, you get a much more interesting result. Of about a 10% ratio. So for every 10 dark matter particles at freeze out, there's one co-annihilating particle. That is not irrelevant. That's something that could, in principle, drive the process of freeze out. That's right.
Does that mean that it would decay into something else after?
Well, it has to, but for this to work, it has to carry the same stabilizing quantum number as a dark matter. Okay. So in a SUSY scenario, the point is that both are parity odd. Okay. So the neutralino and the chargino, if left to on its own devices, will decay to a neutralino in something standard model. But at this point, it's in equilibrium. So it's being produced and destroyed at the same rate. So.
But after freeze out, you're going to lose your X prime.
Anything you have, any X primes you have after freeze out will decay to X's plus something else, presumably quickly. So I can write down an effective cross section as a function of X, where X again is the mass over the temperature for a series of co-annihilating states. The states are going to be indexed by I and J. So here's the annihilation or a co-annihilation cross-section for state I and state J. I can write down the degrees of freedom carried by each in this quantity, which I'm calling Gx, which I'll define in a second. And then these things where the deltas are just defined as the mass splittings from the X particle.
From the X particle?
The dark matter, whatever the lightest state is.
So X.
I'm happy to call that 1 if you're better with that. The lightest one is 1.
So for one of them, it's going to be 0.
That's right.
Okay.
So this G effective is a sum over the particles involved of this, and then there's this exponential, which accounts for the estimate we just did before, which shows that if you have a big mass splitting, you won't have any of these left at the time of freeze out. So this effective cross-section will give you the relic abundance if you treat it like the real cross-section for the purposes of freeze out. And I bet this is confusing right now, so I've got a couple of examples we can consider to get some physical intuition for what this means. So let's say in the first case we have two nearly degenerate particles, x and x prime.
So if x is the mass over the temperature, which mass are we assuming it's close enough we don't care?
Well, you mean in this example?
You've got all these functions of x. You said x is your mass over your temperature as usual, but...
Sure. This is of the temperature or mass of the dark matter. X, yeah, that's right. The lightest state. Okay, so I have two very degenerate particles. And I am going to imagine that the co-annihilation cross-section is bigger or much bigger than either annihilation cross-sections. So all else being equal, these particles are going to deplete themselves through annihilations with the other member of these two species than with one of their own species. Yes? This? So in this case, for example, the particles are degenerate, so this is very small, so this term just goes to 1. It doesn't matter. Okay. X, again, is the temperature over the mass of the dark matter particle. And it evolves. But at freeze out, it's going to be the standard 20. The thing that's 20. It's mass over temperature. Excuse me. Yeah, of course. So the point. Let's look at this briefly because this is important. So if you had a sizable mass splitting, this is a very small number, and that means you're going to entirely reduce this problem to the standard annihilation problem. Co-annihilations won't play a role. If delta is smaller than about 1 over 20, then this term won't be very small, and the co-annihilations are important. So in other words, in order for co-annihilations to be important, generally speaking, you need the mass splitting to be about a 20th of the dark matter mass or less, or maybe a 10th, something like that.
So if it's very small for a large mass splitting, it comes in the denominator.
Good. All right. Let's figure that out. One of my.
Negative, very small number. I feel like should it be plus?
Yeah. Let's check my notes. Well, that is what my notes say.
You do something very small.
Oh! I just forgot a different term. I'm sorry. Good eye, everyone. There. And now it should make sense if you follow it through. Way to pay attention. All right. So let's go to this physical case. The co-annihilation cross-section is much larger than either annihilation cross-section, and the mass splitting is irrelevant. It's a 1% or less, or 5% or less of the total masses involved. In this case, G effective just reduces to the sum of these of the individual particles' degrees of freedom. And the effective cross-section reduces to the co-annihilation cross-section times the following ratio of degrees of freedom. If GI and GJ are the same, this works out to about a fourth or to a fourth, and we have the co-annihilation cross-section over 4. So you can imagine a situation where the dark matter annihilation cross-section is essentially 0. It's many orders of magnitude lower than the thermal benchmark estimate, but this co-annihilation cross-section is maybe 8 times 10 to the minus 26. That will give you exactly what you want in terms of relic abundance, but it will give you essentially no signal for indirect detection. And for the sake of time, I am not going to go into my second example on the board, but I will just say it in words. You could imagine a different situation, again with the small mass splitting, but in this case, let's reverse this. So now the co-annihilations are not relevant. Intuitively, what's going to happen in that case? Can anybody just kind of think it out without working it out on the board? Well, the X population doesn't really know or care about the X prime population, and vice versa. So the X's are going to freeze out, and then entirely separately, the X primes are going to freeze out, about at the same time.
The X primes are going to decay into X's.
And then the X primes are going to decay into X's, enhancing the population of X primes, or of X's, enhancing the relic abundance, which means to get the right relic abundance, you are going to need a larger cross-section. So in that sort of scenario, the prospects for indirect detection are enhanced, not suppressed, as a result of what you could broadly call co-annihilations. It's almost like a late time decay scenario, but these equations cover that as well.
When you say late time,
I mean after freeze out, that's all I mean. Okay. So let's make a list of sort of scenarios we've been talking about. We talked about P-wave amplitudes and their suppression. We talked about resonances. We talked about co-annihilations. Not going to go through a calculation, but I'm going to say in words what asymmetric dark matter is. So if you tried to do the thermal relic abundance calculation that we talked about on Monday for the case of normal matter, like baryons, you would find that there should be no atoms in the universe today. Essentially none. The fact that they exist tells us that there must have been a primordial asymmetry between the number of quarks and antiquarks, or at least matter and antimatter in some sense. And the annihilations stopped earlier than the thermal relic abundance calculation would generally lead you to expect, because you ran out of antimatter to do the annihilating with. So once you have depleted all of the antimatter, you're stuck with just matter and it doesn't annihilate. You can imagine something analogous to this goes on in the dark sector. We don't have any evidence for this, but it's a logical possibility. So you can imagine there's dark matter and anti-dark matter. They start out with different abundances. When the smaller component disappears, the annihilations stop, and that's what sets the relic abundance today. So what does this mean for indirect detection, if that were the case?
it'll be extremely difficult because it stopped annihilating because there was no anti-dark matter left. And so unless you're creating anti-dark matter, there'll be no signal.
So today we'd have a universe that's filled entirely with either dark matter or anti-dark matter, one or the other. And in the scenario we're talking about, that can't annihilate. So you would suppress or maybe set to 0 any annihilation, so you could consider. Depends exactly what makes it symmetric or anti-symmetric, but you can find exceptions to this, but that is the general feature. So that could very strongly suppress indirect detection searches. Let's see. I could imagine scenarios where the dark matter is generated not as a thermal relic, but through a late time decay of something. All I mean by late time is I am imagining some particle that is sufficiently feebly interacting that at some point it stops interacting with the bath and freezes out itself, and after doing so, decays to the dark matter, or to stuff including the dark matter. A popular example of this are moduli. So in a wide variety of theoretical setups and scenarios, you expect there to be moduli, and these things have very, very feeble interactions. Oftentimes they can come to dominate the energy density of the early universe, and then long after they've frozen out, they decay, populating the universe with whatever kind, your favorite kind of WIMP. Okay? And this would populate that population after the WIMPs would have frozen out thermally. So you could imagine these particles having any variety of cross sections, basically. Now there should still be a thermal abundance. So if the cross section were too small, you would still expect to overproduce the dark matter. So in general, late time decays lead to enhancements of the annihilation cross section relative to your naive thermal benchmark models. Does that make sense? I know I went through that quick. I'm trying to do the last 3 lectures in the last 20 minutes, so it's a little bit tricky. All right, adding to this list. We can write down Sommerfeld enhanced models. So what I have here is an idea or a class of scenarios where there's a mediator that is much lighter than the dark matter itself. And maybe in the early universe, something like this set the relic abundance. So at, in higher temperature environments, this is the leading diagram. But now you go to the very, very low velocity environments of the galactic halo, for example, and you ask whether other processes could be important. Well, it turns out that diagram is enhanced by that diagram, for example. So I've now 2 extra W's being exchanged there. And it starts to look, in this case, when the W's are much lighter than the X's and X pluses, this starts to look like an attractive potential, kind of Yukawa-like. So you can think of this, and I can write down an arbitrary number of those W's going, even number of those W's going back and forth. And this looks like a Yukawa potential, kind of like those 2 dark matter particles are forming a bound state as they annihilate. And that can enhance this cross-section a great deal. It's a complicated numerical calculation, but oftentimes you find cross-sections which scale like 1 over the velocity squared, which for velocities are 10 to the minus 3 in the halo is a big number in some cases. I don't think you get factors of a million literally, but you can get factors of 10, 100, even 1,000 or something like this enhancement in certain configurations. So generally, the models that benefit the most from Sommerfeld enhancement are multi-TV models. Winos and Higgsinos and SUSY models are, have interesting Sommerfeld phenomena, and other sorts of models in the literature as well. Okay, so that's a bunch of exceptions that I wanted to convey about the thermal relic calculation. So I have 2 different things I could talk about for the last 15 minutes. I will leave it up to democracy to decide which one. I could talk about A, decaying dark matter, especially in the context of sterile neutrinos in the 3.5 keV line. Or I could talk about hidden sector dark matter models in which annihilations don't proceed to standard model particles but to something else. Who prefers the decaying dark matter in sterile neutrinos and X-rays? All right, and who prefers the hidden sector models? All right, hidden sector models win. Democracy also elected Trump, so don't be so proud. I'm allowed to say that?
It was not like a
Huh?
not the popular. So what you're saying is that what we need to do is bring electoral college to the grid.
Yeah. All right, so sometimes people call this class of models hidden sector models. That's what I tend to call them. Some people call them dark sector models. Some people mean different things by these words. We haven't settled on a well-defined nomenclature. That's also true for the word WIMP, by the way. People use that word to mean a lot of different things. But I'll tell you what I have in mind. I have in mind a scenario where I have some dark matter, and it doesn't annihilate in the early universe primarily or significantly to standard model states, but primarily instead to some other state that is unstable that within the dark or hidden sector. Okay, so the point is all of this stuff is uncharged under the standard model. That's the sort of guiding principle. So this is motivated in part by, if I take the standard sort of annihilation case where I'm going to standard model states, okay, and I take that and turn that diagram on its side, I can't avoid, in most cases, getting a direct detection cross-section. Okay? If you annihilate the standard model particles, then unless you're annihilating entirely to neutrinos or something like this, you invariably wind up with an elastic scattering cross-section, and those experiments have become so sensitive that you have to work kind of hard to explain why you haven't seen it. Now, there are plenty of exceptions, and if I was giving a talk on that, I would give you a bunch of those exceptions, just like I gave a bunch of exceptions about the annihilation cross-section in direct detection experiments. But this has motivated people to consider cases where this is not the sort of process that drives freeze out. Instead, something like this is. So let's consider a couple of limits. Let's say the let's imagine you're in a limit where the two sectors, even though they don't share quantum numbers and they can't annihilate into each other, they can scatter off of each other enough to maintain kinetic equilibrium. By kinetic equilibrium, I mean the temperatures of the hidden or dark sector and the standard model sector are the same. This is pretty easy to do. For concreteness, let's just imagine that my X is a Dirac fermion and my X prime is like a Z prime, a new U1, and it has some small kinetic mixing with the photon or Z. Okay? I can easily imagine scenarios where that sort of diagram keeps the hidden sector at the same temperature as the visible sector. Now, you might think that I'm cheating here by writing this diagram, but here I have in mind some sort of small parameter epsilon, which is describes the kinetic mixing between the hidden photon and the Z prime. And as long as that's not tiny, this will they'll generally be in equilibrium, and we'll have we'll live well within this limit. If that's the case, what can we say about the annihilation cross-section of the X? The cross-section for XX to go to X prime, X prime. Assuming we want to get the right thermal relic abundance. It will be just like this normal case. Okay? So nothing's different. Okay? I mean, there's some very subtle things are different. The number of degrees of freedom present in the bath are different, things like this. But basically, you're annihilating to a bunch of Z primes or whatever your X prime is, and then those decay to standard model stuff in a short period of time, and nothing's very different. Okay? But what's very different is that you can't turn that diagram on its side and get a meaningful direct detection cross-section, at least if something like epsilon is sufficiently small. Okay, so that's the whole idea here. But now for indirect detection, you're still producing these with the same sort of cross-section as in the standard case, and they still decay promptly to visible stuff, standard model stuff. So you end up with getting indirect detection constraints, which are very similar to those in non-hidden sector models. The exact spectra of the annihilation products are different because now you have a multi-stage cascade. You produce some X primes, which then decay to some boosted standard model particles. You have to do a couple of integrals over Lorentz boost to get the right answer, but fundamentally it's not all that different. And you can explain many of the anomalies we've talked about in these lectures with hidden sector models quite easily, including the galactic center and dwarf excesses. You can explain the anti-proton excess in this way. None of this is very hard. And it's very easy to evade direct detection constraints. Now let's talk about another limit. Where the temperatures of the two sectors are not kept in equilibrium. In that sort of case, you could imagine that the temperatures were simply set by like initial conditions after inflation or something. Or maybe they were in equilibrium once, but at some point this universe expanded, that the Hubble won out over the elastic scattering processes, essentially freezing out the individual temperatures, allowing them then to evolve independently. But it's, like I said, it's also possible you can treat this as entirely initial condition. Maybe when those inflatons decayed at the end of inflation, they only produce standard model stuff, or they only produced hidden sector stuff, or some other ratio. Anything like that is logically possible. So what happens in this case? Let's walk through the early universe history in this sort of scenario. So when they're not talking to each other, the hidden and visible sectors are not interacting, is there anything about the visible sector that impacts the dark sector phenomenology early on? I'll give you a hint. I can think of one way it impacts the phenomenology. Sorry? That's right. So just the energy density in the universe, which determines how fast the universe is expanding. So you have to include that. It's not like the hidden sector or visible sectors are entirely irrelevant to each other, but they're awfully close. So the universe is expanding. This process of freeze out goes on entirely within the hidden sector, with the caveat that the Hubble expansion is determined by the total energy density. So you've frozen out. You have a relic abundance of X's. And now you have a big population of X primes that have been generated in those annihilations. In fact, you have way more of those than you have X's. Let's say, for the sake of argument, that the interactions between the hidden and visible sectors are very, very weak. What does that tell us about the lifetime of the X prime? Long-lived. So what would happen if I have this population of X primes in the early universe, and I'm letting the universe expand while they sit there not decaying or scattering with the standard model? Tell me how.
Because it's a part of the point of freeze out is that you have the annihilation, so you reduce the amount from the equilibrium amount.
So the X primes are going to decay eventually.
But the thing is, if they're not decaying at that time, then you have you're not having a reduced amount of dark matter early on. If they're stable long term, it's going to be much later that you lose that.
So we have this sort of picture in the dark sector. The X's have done this. So this is the X population. They've frozen out in the standard way. The X prime population started out with some similar abundance. It's a little lighter, so it does this a little bit later. And then as these things annihilate, a new population comes in. We have a lot of X primes. Okay. So I don't think this is going to, so far it hasn't ruined the dark matter phenomenology. But as the universe expands, eventually these guys become non-relativistic. So as the universe expands, how do energy densities in matter and radiation compare? matter comes to dominate, right? So the energy density in matter goes like 1 over a cubed. The matter energy density in radiation goes like 1 over a to the 4, and therefore radiation loses, and these things come to dominate the energy density of the universe. By a lot, maybe. And eventually they decay. What happens then? You've dumped a ton of standard model entropy or energy density into the universe, and that dilutes the amount of X's. Okay? It's like you add 1,000 times more energy. That means your effective, the result, relic abundance of these guys goes down by that dilution factor. It totally changes everything you should expect about direct and indirect detection. So what are our prospects for indirect detection in this case? What do we think the annihilation cross-section will look like? Why larger? So let's try a number. So let's say you start with the standard thermal 2 times 10 to the minus 26 cross section. Okay. Then before the late time decay, before the X primes decay, you have what would have been the right amount of dark matter, and then you deplete it, so you have almost no dark matter. So what you need to do to counteract that is lower your cross section, so you started with more of the stuff. So whatever the dilution factor is, you need approximately that much smaller annihilation cross section. So this can suppress your annihilation cross section almost arbitrarily. Well, that's not really true, but by factors of hundreds or thousands possibly. If the decay happens during or after BBN, everything's ruined. So we're not considering that. But you could imagine this is all going on longer, much before that. That's totally plausible. So I will simply say that there's one way in which indirect detection might be saved in this sort of scenario. You could imagine, well, and you should imagine, that during this early phase of matter domination, when the X primes are dominating the universe as matter, non-relativistic matter, structure formation will occur in an entirely different way than in the standard picture. So in standard cosmology textbooks, perturbations, I just need a little more board space. Perturbations like delta rho over rho grow as the log of the scale factor in radiation domination. And they grow with the scale factor in matter domination. We've got, in this scenario, an early period where this grows a lot faster than in the standard picture. So what kind of changes should we expect this to produce in the universe today? On what sort of scales might we expect this increased structure to be found? Enhanced degree of structure to be found? What? Very, very small. Okay, so this is in the early universe. Hubble expansion was very fast, and therefore the horizons were very small. And it turns out this is going to be like tiny, tiny little clumps of dark matter that make up the halo. Much smaller than anything we have the ability to measure. But this is the good news for indirect detection. I look at a dwarf galaxy or something. If I could really look at it closely, much more than we have any ability to, you would find that it's not a smooth gas of particles, it's a smooth gas of clumps of particles. And those clumps are going to be annihilating like mad in a way that can quite significantly outperform or exceed the suppression we just talked about. So this is complicated, and hidden models lead to a bunch of interesting indirect detection phenomenology, much of which has not been worked out yet. But expect this to be important in the indirect detection landscape in the years ahead. This is where I think a lot of the research is going to go. All right, so we're a little late for lunch. Are there any questions before we call it a day? Or at least a morning?
So is this, are these last statements that you made about like dark matter coming so is this generically true anytime you have any sort of interesting matter domination and it goes back into radiation domination?
I think changes in the structure formation history are generically expected in that class of scenarios. There are lots of ways it can play out, though. It depends on exactly the ordering of things. For example, you could imagine scenarios where when these X primes decay, they actually destroy the halos that they created. But that's in certain parameter space that's important. In other cases, it's not. So it's very subtle, and there are lots of different limiting cases. But it is generically expected that the small-scale structure of our universe will be very different in any scenario with an early matter-dominated era, which is a generic feature of a lot of hidden sector models. Or I should say highly decoupled hidden sector models. That's where it's a generic feature. Yes?
Would it be possible to see this on the multiple spectrum and so?
So we're talking about like sub-parsec scales. Okay, so we have no way to do this yet. Now, I don't know about the far future. I'm happy to speculate about what cosmologists will be doing 100 years from now, but nothing that I expect to happen with any foreseeable experiment will be able to see this sort of effect.
Since the rate of expansion of the universe also is significantly different between matter and radiation dominated, would this not throw off the sound horizon if this is happening so
So
early?
all of this is happening long before anything that impacts the CMB.
Okay.
So if something like this were happening 10,000 years after the Big Bang or something, yes, absolutely, you would screw up everything. Here we're entirely protected in the sense that the CMB is not measuring modes that are in the scales that we're talking about. Okay, it's been a pleasure. I've enjoyed these lectures. I've enjoyed meeting so many of you, and I look forward to talking to you for the rest of the day and night.